welcome everyone. Let's get started. I'm Anders, lead Android developer at BonTouch. I'm joined by my colleague Carlo, who is an iOS tech lead also at BonTouch, of course. The agenda for today is as follows. We're going to give you a little bit of a background of who we are and the product we are working with, and then we'll give you an introduction to conflict-free replicated data types, or CRDTs, and show you a little bit about how you can implement them yourself. We're also going to show you some examples from our data model and some methods of resolving conflicts that we've done in our data model as examples for you, and also share some details from our technical solution and the learnings that we've had along the way. But to begin with, what is BonTouch? We are a digital design agency. We primarily work with established brands to create great experiences for their end users. This typically takes the form of native mobile apps, but of course there's lots of other digital partnerships that we do as well, and of course like design and everything as well. Some of the services that we do at BonTouch, you can see here, a lot of these are some of the most major brands in Sweden. But Carlo and I work with the Post-it app. So Carlo, can you tell us a little bit about the Post-it app?
Yeah. So with the Post-it app, user can capture physical notes and essentially turn them into digital objects. The notes can then be arranged in boards, edited, and so on. And users can also create digital notes from scratch, drawing or typing some digital text. And they're also native apps, so they run on iOS, Android, Chromebook, and so on. Last year, we received a Material Design Award from Google in the motion category, which our team is very proud of. Let's talk about our existing technical solution. We have a capture engine that is shared across platforms, and this is written in C++ and based on OpenCV. And this allows us to detect and extract Post-it notes from photos. Users can also export their notes to services like Trello and Miro, generate PDFs, and so on. And we also have a custom file format that users can export and import into. On iOS, we also support iCloud sync between Apple devices, but we currently have no way of syncing between Android apps other than exporting and importing again. We also don't have a web client. So what was next for us? We had two desires mainly: a web client and the possibility to sync boards across different devices and platforms. And this meant that we needed a way, a model that we could use to sync this data and a way to leverage it across different platforms. So today we'll talk about what we learned on the way there. As a first step, the Post-it brand has collaborated with Microsoft, and we've launched the Post-it app for Microsoft Teams in the US just a few weeks ago. What you're seeing here is a web app running inside Microsoft Teams with Kotlin Multiplatform code. And this enables real-time collaboration on the same board, communicating over WebSockets. We've also launched a mobile app that allows you to send captured notes directly into the shared board. But so, because this product is all about collaboration, we needed a robust way to sync these changes between clients. So you might have seen a software that looks a little bit like this. Users are asked to manually pick a version whenever there is a conflict. Obviously, we didn't want this. Not that this is bad per se, but it's not what a user would expect in an application like ours. We can't interrupt their flow, asking them to resolve conflicts all the time. So this is our scenario. We have multiple nodes that need to communicate. They could be computers, web browsers, mobile clients, servers, and so on. Whenever there is a change, a state is replicated in all of our nodes, and we need a way to ensure consistency. Nodes might also come and go, or perhaps send changes at later times. So in summary, we have multiple users that need to be able to collaborate in real time. We don't want manual conflict resolution, so we need simple and understandable rules for merging conflicts, both for ourselves and for our users. And we also want to store the state locally so that users can work offline. The approach we chose to solve this was conflict-free replicated data types.
Right, or CRDTs for short. We all like abbreviations. I'm going to give you like an introduction and motivation for how it works and why it works, but obviously we won't have time to go into all the details, all the different types of CRDTs, and all of the formal proofs or whatever. And of course, I should also mention we didn't come up with this. It's been around for a few years and successfully used in various other services. But when we're talking about syncing changes in this way, there are some properties that we would like to fulfill that will make our lives a lot easier. For one thing, we want them to be commutative, which essentially says that the order in which we perform changes doesn't matter. So if I have state A and Carlo has state B and I receive state B from Carlo, I merge those two changes, then I should have the same result as Carlo having state B and receiving state A from me. So it doesn't matter in what order we received them or had them from before. We also want them to be associative, which essentially says that if we have partial state updates, then we will eventually reach consistent states. So as long as we've all seen all the same set of changes, we're going to end up in the same result. In this example, if you have seen states A and B and combine those, and then you see that you receive state C, you should have the same result as if you had some other combination of states from before. And finally, we also want them to be idempotent, which says that changes are only ever applied exactly one time. So even if we receive them multiple times, we're only going to apply them once. So if we can fulfill all three of these properties, we're going to have a really easy time as developers, because we can essentially send these updates in any order. We don't need to care about the recipient, what they have seen before, what they haven't seen before, and we can even send them multiple times, just spam them out on the network if we were so inclined, and we would eventually still be consistent. So this makes things a lot easier for us. As an example, if we consider we have a state consisting of one integer, we might sync it by sending deltas around, like add 10 and subtract 31. This is associative and commutative, the standard rules of arithmetic, but it's not idempotent, of course. We could perhaps add that by adding some kind of unique identifier to every change, but we don't really want to be sending operations around. We'd rather deal with states. This is also something called convergent replicated data types. So the idea is we're going to send states around instead of operations, and we have a merge function which fulfills these properties that we can use to combine states. So if we have two prior states, we can combine them to form a new state. And of course, this combination should take into account the changes that were present in both states in whatever rule we want to achieve. You can think of this merge function as like our strategy for resolving conflicts. So as an example, this is a very simple CRDT, the grow-only set, or the G set, which is a set in which you can only insert elements, but you cannot delete them, and the elements must be immutable. But of course, the merge function becomes very simple. It's just a union, and you can see for yourself that, of course, it fulfills these three properties that we wanted. So this is a very simple CRDT, a very easy implementation. But generally, so far we've already talked about integer deltas or a set of immutable data, and that's it's hard to build a data structure from that. Usually, the way we think about mutable states in general is that we have an object with some mutable property that we can write to, and whenever we're reading from that property, we're reading the last written value, whatever was last written. It's the same principle here, but we could have multiple writers, but we should still see whatever is last written. To do this, we need an ordering of changes so that we can all agree, all the nodes can agree, what was actually the last write. Essentially, we want something like this, where we can construct a timeline that is the same in all the nodes, so that we can all agree on, yes, this happened, and this happened, and this happened. So in this example, the color should be orange because that was the last thing that happened in our timeline. So as long as every node has seen the same timeline, they're going to reach the same final state. So if we try to form this into a CRDT, essentially what we're going to do is we're going to tag every change we make with some order or a timestamp. And we'll talk about what we mean by timestamp in a little bit. The merge function is very simple. We're just going to pick the property or the change that has the greatest timestamp, the latest one, right? And it's fairly easy to see that it fulfills all these desired properties. But so this timestamp, what do we mean by that? So we need to talk a little bit about clocks, because we need a reliable system to place events in our timeline. We could use the physical clock, which is simply the device time. Maybe it measures number of seconds since the Unix epoch or something like that. And the problem with this is the device clock or the physical clock can, of course, jump in time. There's things like leap seconds or corrections from network time, or maybe the user is changing their clock. Even if we're using network time, all of our nodes are not necessarily going to be exactly at the same time. There's always going to be some kind of drift. And that might be fine, but given that we're talking about like a real-time system with multiple users, these events can happen close together in time. So this drift could actually be significant. And finally, we don't actually control the clocks on the devices. So it's not like we could just say, yeah, you have to have network time to use this application. We can't really enforce that. There's also things like logical clocks, which keep track of happens before relationships, gives you like a partial ordering. So first this happened, then this happened. And essentially, it's just a counter that you would increment for every change. There's a couple of different types of these. I'm not going to talk about them in detail, but in general, they require either that you have a constant communication between all the nodes to synchronize on what is the counter value right now that we all agree on, or we require that the timestamps would require storage that would scale with the number of nodes in the system. We don't have a known number of nodes. Every time a new user joins a board, we would have another node, right? So we don't want the timestamps to keep getting larger over time. So instead, we use something called a hybrid logical clock, which, as you can see, has bounded space usage. It consists of 3 things. We have a physical time from the device clock. We have a logical counter that allows us to essentially tick the clock even if our local time is behind, and I'll show you an example of that later. And we also have this tiebreaker value, which is simply in the case that the first 2 happen to match, there's 2 timestamps where the physical time and the logical time happen to match, we can fall back on the tiebreaker to keep a stable sort in all the nodes. So it's just some arbitrary value that we can use. And we'll see samples of this implementation. But in the hybrid logical clock, then we're going to keep track of the greatest hybrid logical time we've seen from any node. So what is the greatest time right now? And we can use this counter to increment our timestamp. So I'm going to show you an example of that. In this example, we have 2 nodes. You can see that one of the nodes is behind, its device clock is behind the other node. You can also see on the left there, we're going to keep track of what is the greatest hybrid logical time that we've seen. So let's say they start making some changes. They're going to update their clocks with the greatest time they've seen. So far, they haven't communicated, so there's nothing weird going on so far. We're just keeping track of these values. But let's say the second node is going to send its change to the first node. And when we do this, we need to update our clock. Because remember, our clock needs to represent what is the greatest time that we've seen from any node. So we're going to do that. We're going to update it because this is a later time than we've seen before. And now, when we want to make another change on this first node, we're going to notice that actually our local clock is behind. And instead of using our physical clock, we're going to use the same timestamp that we've seen before, but we're going to add one to the counter. We're going to say it's 12:43, but it's 1 later than that, right? So this allows us to keep ticking the clock without, even though our physical clock is behind. So once our physical clock will catch up, we can start using it again. One thing that could happen is this scenario is similar to the first one, where we have 2 nodes that are behind the third one. So it's going to send its changes to the other nodes. We're going to update the clocks as usual, and then we're going to make changes on both nodes. And now we've actually ended up in a scenario where we have 2 timestamps that are identical, outside of the tiebreaker value, which is why we have the tiebreaker value. But essentially what's going to happen here is, this value is just going to assign a random ordering. Essentially, it's arbitrary which one we pick. We're just going to pick one kind of at random based on what was in the tiebreaker. So you might think this is kind of like a problem or a cop-out or an error that's just part of the system. We just kind of have to deal with it. It's the best we can do. But actually, that's true too. But in an actual real sense, it's perfectly valid. So we'll talk a little bit about causality or happens before. So in this scenario, we can say that event A was known to both node 1 and 2. So whatever changes they make, B1 and B2, we can establish that there is a causal relationship. A happened before B1 and A happened before B2. But there is no causal relation between B1 and B2. These are concurrent and independent events. So it really is like, in a physical epistemic sense, there is no way for us to know which one happened last. They could be happening at exactly the same instant, for example. So it really is arbitrary which one we pick. We just need to ensure that that we're picking the same thing, and that's why we're keeping this third value that we can compare, so all the nodes know which one is the last one. Okay, So now we pretty much have everything to start implementing our CRDTs, and I'll show you some Kotlin code examples. Most of this is going to be a repeat of the algorithms that we talked about, but I'm going to show you the code so that you can see that it's not a lot of code and it's not very complex code, but don't get too hung up on the details. But let's start implementing a hybrid logical timestamp. So this is just a simple data class that consists of these three values as described. We're calling the tiebreaker node here because we're going to have a unique value for every node. And the types don't really matter that much. I've used string, for example, for the node, but it doesn't really matter as long as we can compare it. So of course, you can see we're implementing comparable, and we're going to compare them in the order as listed. Next, we're going to implement a hybrid logical clock. We're going to abstract away the physical clock, both for Kotlin multiplatform purposes, but also we can supply a fake clock in our tests, for example. You'll also see that we're passing the node value that this clock should use, which is the tiebreaker, as mentioned before. This is just some unique value for this node. It could be random, it could be server generated, it could be based on hardware keys, whatever. And we're also going to have this reference that keeps track of what is the latest time we've seen from any node. There's two operations we can do. One of them is to update the clock with the time from another node. So it's very simple. We just need to take whatever was the greatest value, right? Just pick the maximum time. The second operation we have is to get a new timestamp. And there's two things we want to fulfill with this function. The function, whenever we return a timestamp here, it needs to be greater than any other timestamp that we've seen before. And we must receive strictly increasing timestamps every time. Like if we call this within the same nanosecond, we still should receive increasing timestamps every time. So there's, as mentioned before, we're going to compare the physical time from our local clock to the one the greatest one we've seen before. And there's two things that could happen. Either our physical time locally is greater than any other nodes, in which case we're fine to use our physical time. We can reset the counter, and we're going to use this tiebreaker value that we've defined. Or we are behind some other node's clock, in which case we can just tick the logical counter and also supply this tiebreaker value. Now we can implement our last right wins policy. In this case, we're creating a mutable class that holds a value and a timestamp. And then, of course, the only thing we need to do is only update the value if the timestamp is greater. I'm showing it here as a mutable type for simplicity, but I would strongly recommend using immutable types. We'll talk about that a little bit later. We also, as mentioned before, we're going to add things to grow-only collections, so we're not going to be able to remove them from the collection. As you might imagine, if we do that, it's just going to come back whenever someone else sends their state, right? So instead, we're going to keep track of the fact that they're deleted with a property that we can change. So we have this like tombstone that tells us this object's actually deleted, and we could filter that out on the collections as necessary. But let's create a class that uses this. So we have this user class, we have an immutable ID on it, and we also have these free properties such as name, age, and deleted. You can see we're always passing these default values to use. And then we can start replicating this in all of our nodes. So what we mean by replication is that every node has its own local state. So on the first line, you can see we're creating a mutable map that will hold all the users that we have. Let's say we have received this message from another node that tells us, user with ID 123, I want you to update, I've updated the property name, and I've set the value to Alice with this timestamp. So we're going to look in our local map to find this user. If it doesn't exist, we're going to create it. So there's no explicit creation. We're just going to assume, okay, we're receiving a property for something we haven't seen before, we're going to create it. And that's why we have these default values. Finally, we're going to look at this message we received and figure out, okay, which property do we need to update and what do we pass in. This is a little bit sort of simplified regarding type safety, and of course in a production implementation you would probably want this to be a little bit more, you wouldn't have these hard-coded strings in this when clause, for example, but it illustrates the principle, right? So this is happening in every node, so as long as we've all seen the same messages, we're going to have the same local state. But what do we mean by conflict-free? I mean, it's not magical. It can't just resolve conflicts for us. So, of course, there's no such thing as conflicts, but that also means that could be a problem because it doesn't actually surface the fact that there were simultaneous edits to this, for example. So some changes might be lost, and we might consider that a conflict. or we might end up with data in an unexpected state, and this might be due to dependent properties or references to other objects that are also changing underneath us, right? Or maybe we have references to outside data sources. Yeah.
Right. So I want to talk about our data model a little bit, and I'm not going to go through the entire thing, but I want to mention some mistakes we made along the way and how you can avoid them. So these were our rules. New objects are added to grow-only sets. Deletions are only marked. We never actually remove anything. And updates to independent properties are applied using the last writer wins policy. But most importantly, models should be designed so that ambiguities are not just unlikely, but completely impossible. So the first example I'm going to talk about is positioning nodes. Nodes can be placed either directly on a board or within a group. If they're placed within a board, then they have global coordinates. If they're placed within a group, then they have local coordinates relative to the group center. When placing a node inside a group, it's important that we don't confuse local and global coordinates. So this was our first approach. We have an X, Y positions, and they're separate properties. And then we have a group ID that can be null. And if the group ID is null, then we know that these are global coordinates, and then the nodes should be placed directly on the board. Otherwise, if we have a group ID, then we know that the coordinates are relative. But the trouble is that these properties aren't truly independent, but our model still allows us to update them separately. So what can happen is that two users concurrently update the model, and we end up in the wrong state, or even an illegal state. In this case, two users might be updating the position of a node at the same time. And the top one, for instance, is moving the node from the board into a group, so it sends an update with local coordinates. And the bottom one is moving the node within the board, so the update only contains absolute coordinates. So if the top update ends up last, everything is fine. But if the bottom one ends up last, we end up with a mix of both updates that don't really make sense together. So our node will have absolute coordinates while also having a group as a parent. And this is not what either of the users wanted, and we might even break our UI. One solution could be to always specify group null if we're using absolute coordinates. But an even better way is to use a single placement property. And this ensures that updates to a node position cannot be misunderstood, right? Developers are forced to always specify whether the coordinates are absolute or relative to a group in the same update. So in addition to X and Y positions, we wanted a stable and editable Z ordering of objects so that users can rearrange objects on top or below others. And we always want to be able to insert an object between any two others. But we can't reset the Z indices of all objects. There might even be new objects that we don't know about and therefore can't update. This means that our Z index can't be a simple integer value. If we use a float value instead, we can always find a value between any two others. But you can already see that eventually, if we keep doing this, we'll end up losing precision and get floating point errors. So instead, we wanted unbounded precision. So we ended up using something called fractional index, inspired by Figma. And it works a little bit like Java's big decimal. It's still a real number, but it's stored as a string. And here, more precision simply means that the string will be longer. And for efficiency, we store in base 63. It's still possible for two objects to end up with the same Z index, but in that case, we fall back on the object's identifiers. Because the important thing is that the behavior is consistent across all clients. Another interesting problem was with groups. So what happens if someone resizes the group while another user adds a new node to this same group? You can see that we can't just apply both changes directly, otherwise we'll end up with a group that is too small for its content. Instead, in a data model, it's not enough to just read the size of the group, but instead we have to read a computer property that is constrained to be at least as large as its content. So because we have a dependency between the size of the group and the node it contains, and we cannot guarantee it in the data model alone. One more challenge was when we started implementing image layers. So nodes can have digital text, but they can also contain drawings. and therefore we need to handle bitmap images. But obviously, we don't want to store these images in the CRDT state. We need to be able to send changes around in real time. So we want the changes to propagate as quickly as possible. Instead, in the CRDT state, we only store identifiers of the image layers. And then we keep the bitmap data somewhere else. This is an example of external data sources. So it works a little bit like this. Every time a client updates the image, they generate a new ID and set it to the CRDT state. And this tells other clients that the previous image layer is no longer valid. At the same time, we upload the image out of bounds using a simple REST API. And whenever we're done uploading, we update a grow-only set with the layer ID we had generated before. And this tells other clients that the new image is now ready to be downloaded and displayed. We also have some additional data that is sent around between clients, but that is not stored in the CRDT state. We call these transient events, and they include things like cursor positions, selection states, drag events, and so on. Perhaps the most interesting set of transient events is locks. So although the system is designed to work well asynchronously and even offline, when we do have real-time updates, we want to take advantage of that to improve the UX. So we lock objects with a transient event that indicates that someone else is manipulating that object. And this is, of course, a best effort approach. Events might come too late or never arrive at all, but as we saw, we already have a way to deal with conflicts automatically, so it doesn't matter. Another feature we wanted was undo, redo, but how this should work is not straightforward in a collaborative context. When a user wants to undo, there might be other changes on top of theirs made by other users. However, we always want them to be able to undo, and this might mean undoing changes made by other users. They should always be able to get back to what they saw before, which might mean also redoing changes from other users. So you can imagine how this can get quite tricky. Figma has an excellent blog post on this that I highly recommend.
Cool. Let's talk a little bit about the technical decisions we made along the way. Of course, we used Kotlin Multiplatform. We didn't just have a desire, we had a need to have the same code running in all the platforms. It was imperative to the correct functioning that we were all running the same code. We didn't want to write the same code multiple times and find bugs and make changes and then verify all of that. And every time we add more features, we have to update it in multiple places. We had prior experience with sharing C++ code. But of course, using C++ code is not ideal for all the platforms, and I mean, who wants to write C++? We were already using Kotlin in Android and in the backend, so Kotlin Multiplatform was an obvious choice. And it also, it targets all the platforms that we needed. So plus, we have the Kotlin expertise in-house, so it's nothing new for us to learn. So when talking about sharing code, you can kind of think of it as a spectrum between no shared code at all, you're writing the app multiple times, or you have just one app and it's running on all the different platforms and probably you're also sharing the UI there. Breaking it up a little bit more fine-grained, you might think of shared code as a library. So you have some kind of thing you're trying to solve and you're going to add some shared code for that. Or you might build sort of a full-fledged feature with all the interactions and business logic and just swap out the UI on each platform, for example. In our case, we opted to write it as a library because we did not feel confident that we could design a full feature in shared code and make decisions on layout and rendering and caching and animations and interactions and whatever else that could cover all the platform's needs. Like, I don't think that would have been advantageous to us time-wise, all this overhead making the changes in shared code. So we thought it was best to let each platform own the feature and just rely on this library to do all the implementation details. So we call this the core library. We wrote it in Kotlin Multiplatform, and it contains all the data models and CRDT implementations and the operations and utilities that you need, very similar to the code we showed before. We put it as a separate repo. We have, of course, tests for all the different targets, but we're not like putting it in our, we don't have a mono repo and we're not putting the shared code into our app code, for example, or in the backend code. Instead, we distribute it as artifacts for different targets, so pre-built artifacts using Maven, NPM, and Swift packages. And this was actually really good for us because it meant that we had to think about it, as versions. They're artifacts that we're delivering. So assigning versions to them was really helpful to us because we could say things like, yeah, but are you running, version 0.14 of the core? Oh yeah, we updated the backend to 0.14.2, and here's a change log of what's changed, and we fixed this bug in this version. Are you running that version? So it's really, useful for us to actually think of it as a deliverable, almost like a third-party library, but of course it's first-party. Some principles in the implementation. First of all, I mentioned this before, immutability is key to the thread safety, but also like correctness in terms of centralizing or doing safe modifications, because we need to like notify all the listeners. We might need to construct WebSocket messages for the other clients, that kind of thing. And we used Kotlin immutable collections, which also they have this concept of a persistent collection wherein you can create very efficient copies. So if you're copying or you're making a change to an immutable set, you have to copy over all of the contents of the set and then add the element. But in this case, you can reuse the previous set and just add that element, so it's much more efficient. We also handle all the serialization internally inside of the library, which was really helpful for us. We could keep all the messages and the formats opaque to the clients. We could, change serialization strategy without anyone needing to know about it. We used Kotlin X serialization for this. And we also kept the library self-contained with well-defined entry points. So we have a fairly small interface, which I'll show you in the next slide. But basically, it's like you tell the core, I want to do this change. The core might inform you about some events happening, like, OK, here's the new board, for example. And here's, by the way, here's a message for you to send to someone else. So that's one example. We could have had our WebSocket implementation inside of the core library because that was something we knew we needed in all the clients. But actually, we felt it was best to leave that implementation to the platforms because, again, we didn't want to take too many decisions on their behalf. Architecturally, this is a greatly simplified image, of course, especially on the backend side. But you can see that we have a client-server model, as usual. It's not a peer-to-peer thing. And it's quite useful to have the server as an option to be the source of truth or to make decisions if needed. You'll also see that we have the core library present in all the clients as well as in the backend. So what might happen is, on the clients, the user creates a note, tells the core library that I'm creating this note, here are the properties. The core library then decides, OK, here's a message for you to send to the backend. We can pass that along through the WebSocket. The backend will just pass it into the core and receive back some state. Like, this is what happened, and it could, maybe store that in some way. And then also, it probably will tell the backend that, by the way, you need to inform the other clients about this change, and gives it a message to pass around. And the other clients can then receive that from the core and display that in their UI so that we see the same thing. When a client connects to the backend, they will receive an initial merge, as we call it, which is we're sending the full state that the backend has to the client. So here you go, here's the full state. And we can use these CRDTs to calculate the deltas, like what changes have we made locally that the server doesn't know about yet. Obviously, if we made changes that are then superseded by changes that were already present in the backend, we don't need to send those. But any changes that we do have that the backend needs to know about, we can send those over. And after this, we don't need to send full states around. We can just send the changes because we know we have these CRDTs. They're always going to be, being consistent everywhere. I can also mention that with offline support, we're talking about distributed computing, so by necessity, we're not going to have like constant communication. If nothing else, we're going to be separated through time and space. So offline support was extremely simple for us. There is no complex syncing logic. If you've ever written your own like syncing logic manually, you know that it's like really error prone. You have to be very careful. You need to think about all these like edge cases and how you can make sure you're not losing data, for example. But in our case, we just needed to persist the local state, of course, recognize when we're unable to send changes to the backend, and simply reconnect, perhaps using our work manager job on Android, for example, to, once we have connection again, we can send this to, we can connect to the backend, receive the initial merge, and send our changes. And at that point, we're all synced. Yeah, so we'll share some learnings from having implemented this a little bit we want to share with you. First of all, like CRDTs work really well in real-time and offline scenarios, but it depends on your conflict resolution requirements. If we had a situation like Git where, if Git was picking the lines of code for you, I think that would not be a great experience. But in some scenarios, you don't want to interrupt the user with these conflicts. And of course, they can't solve the conflicts for you by themselves. You still have to design your data models to be robust. But it's a very easily understandable framework. And I'll also note that we haven't shown you all the CRDTs that are available out there and all the clever algorithms out there. I would also say that in multi-platform, start with code that you need to share, and then add functions that are unequivocally things that you want to share. So that's why we called it like the core library. It was initially just the CRDT core. But maybe we came up with, we want to be able to arrange the nodes in all the clients. Okay, that's something we can add to the core because we know we're going to need that. But rendering logic or WebSocket connections, it's something that they probably need to do, but we don't want to take that decision in the shared code.
And Kotlin Multiplatform works excellently for JVM and Android targets, which already run Kotlin, but it doesn't always translate well to Swift or TypeScript. And you may think that you can just write tests in Kotlin, verify that everything works, and be done. But actually, that's not enough. You need to, your functions might not be callable from other languages, or worse, perhaps they have wrong signatures, such that you pass the wrong objects and then you get runtime crashes. In general, the ergonomics isn't always great, and there's a lot of trade-offs to make. One thing that we ended up doing on iOS and web was often to wrap Kotlin types, which of course makes the API nicer to use for platform developers, but also introduces overhead. In other cases, we ended up extending types and functions from the shared library, adding platform-specific code. And too often, it was the Android devs writing the shared code, so they were less likely to notice platform-specific issues. And for the web specifically, if you need to use and refer to Kotlin types in the rest of your code, our recommendation is actually to use Kotlin.js throughout instead of a layer of TypeScript. Instead of going from Kotlin to TypeScript and eventually to JavaScript in the browser, it might make more sense to stay in Kotlin land all the way to the browser. Kotlin and TypeScript are very different languages. Some things don't map one-to-one or can't be mapped at all. So if you're already using a language to transpile to JavaScript, in theory, you could just pick Kotlin just as well as TypeScript. And of course, this depends on your web devs. Most web devs are happy already with TypeScript, so there could still be good reasons to prefer TypeScript. And finally, we realized how important documentation and knowledge sharing can be. Most iOS and web developers are not familiar with Kotlin or the toolchain. But we saw this actually as a great opportunity to collaborate more with the Android developers. We used code review, for instance, as a way to spread knowledge, and we made sure that we kept the detailed documentation easily accessible. So you can see here, for instance, we have the same documentation available from Docker in HTML, but also directly in Xcode for iOS developers. And in general, pretty much everyone in the team now agrees that we couldn't have built this product without Kotlin Multiplatform. I myself was very skeptical at first as an iOS developer, but I have to say I've completely changed my mind. And as you saw, it wasn't always smooth sailing, but in our case, we saw the huge advantage of having not just analogous code, but exactly the same code in all our platforms.
Cool, yeah, that's pretty much it. If you have questions about this, I mean, there's lots of stuff we had to omit for time. So if you want to know more about the product, about BondTouch, CRDTs, Kotlin Multiplatform, come talk to us at our booth. Thank you.